So far, we've looked at a few different factoring methods. We looked at one method that works when there are four terms, that's grouping, and we looked at a few methods that work for trinomials with three terms. We had unfoiling, the AC method, and trial and check. Now we're going to focus on a method that works when there's two terms, but only in a specific scenario. This method involves the difference of squares, and what that means is if we have a binomial where the first term is something squared and the last term is something squared, and we have a difference, meaning that it's a subtraction, anything in this form can be factored into the sum of the two things that are being squared times the difference of the two things that are being squared. We'll look at a few examples and then we'll talk about why this factoring method works. So we'll start off with an example, x squared minus 9. Now this is a difference of two squares. X squared is x squared and 9 is 3 squared. So both of those are perfect squares, and we have a difference here. So because this is a difference of squares, we can factor it into a sum times a difference, and the quantities that go inside the factors are the two things that get squared to become the two terms. In other words, the square roots of these. The square root of 9 is 3. The square root of x squared is x. So when we factor this, it becomes x plus 3 times x minus 3. Whenever we've got a difference of squares and we factor it, the answer is going to be a sum times a difference. Let's look at another example. Let's look at 4y squared minus 121. If we look at each of these terms, 4y squared is a perfect square. It's 2y, quantity squared. 2y times 2y is 4y squared. And 121 is also a perfect square. It's 11 squared. And also this is a difference because there's a subtraction in the middle. So because this satisfies the requirements, it's a difference of two perfect squares, we can factor this into the sum of those quantities, 2y plus 11, times the difference of those quantities, 2y minus 11, and this is our factorization. We're going to do one more. Let's look at x to the 8th minus 81. Now, again, these are both perfect squares. X to the 8th is x to the 4th squared, or x to the 4th times x to the 4th. And 81 is 9 squared, 9 times 9. And it's a difference, so we've got our difference of squares. So we can factor this into the sum x to the 4th plus 9 times the difference x to the 4th minus 9. However, this is a trickier one. We're not actually finished yet because if we look at x to the 4th minus 9, that is a difference of squares, and it can be broken down even further. X to the 4th is x squared squared, and 9 is 3 squared. So that can be broken down or factored even further. The first factor that we had, x to the 4th plus 9, that cannot be broken down any further. Even though x to the 4th and 9 are perfect squares, there's an addition here. It's not a difference of squares, it's a sum of squares. And we cannot factor a sum of two squares using the integers that we've been using. There is something you might see later in a future class involving imaginary numbers, but for right now, we have a rule that says we cannot factor the sum of two squares. But the factor x to the 4th minus 9 is a difference of squares, And we can break it down even further into x squared plus 3 times x squared minus 3. And this ends up being our final answer because none of them can be broken down any further. Sometimes students see x squared minus 3 and think we can break that down because x squared is a perfect square and we've got a difference, but 3 is not a perfect square, so we cannot factor that any further, and we end up with x to the 4th plus 9 times x squared plus 3 times x squared minus 3. Now, some of you might be wondering, why does this work, this difference of squares? And the reason it works comes down to foiling out f plus L times f minus L. If we want to multiply this, we FOIL it out. So the product of the first terms is f squared. The product of the outer terms is minus FL. The product of the inner terms is plus FL. And the product of the last terms is minus L squared. And we notice that the negative FL and the positive FL cancel, giving us f squared minus L squared. So this is a special product. Anytime we have a sum of two terms times the difference of those same terms, we end up with the first term squared minus the last term squared because of this cancellation. And if we look at this in the reverse, it tells us that if we have a difference of two squares, we can factor it into the sum and difference of the quantities being squared.